Hey everyone. So in this video, I'd like to talk about graphs of linear functions. We defined linear functions in the previous video. We said that a linear function is any function of the form f of x is equal to mx plus b. So some constant times your input variable plus possibly another constant. And so here we gave some meaning to these constants. We said that, hey, this coefficient of our input variable, really for a linear function, this is the rate of change of our function, right? So the change in the output of our function divided by the change in the input of our function. And for linear functions, this is sort of a key fact about linear functions, is that the rate of change is always the same between any 2 points on our linear function. That we say the rate of change is constant, and that constant appears as the coefficient of our input variable. So this is a key fact about linear functions, is that they have a constant rate of change. And it also works in reverse. If you see something with a constant rate of change, you're dealing with a linear function. Here we also give this rate of change the name slope as well. So when we're talking about a linear function, the rate of change is really analogous to the slope, the change in the output divided by the change in the input. And we said that this constant here, b, well, if we imagine plugging in 0 into our input variable for this function, what we're going to get out as a result is going to be, well, 0 times m would be 0, and then add that with b, we would get b out. This is like an initial value, the output that we would have for our function when our input is 0. So these are some facts about linear functions. And then another reason why they're called linear functions is, right, if we graph this function here, or any function in this form, what we get is a line. A straight line. Okay, so I want to talk about graphing linear functions, and one way of graphing linear functions is just by plotting points. Whenever we have an equation, we can always graph that equation by finding solutions to that equation, giving us an ordered pair, and then plotting that point on a coordinate plane. And so here, let's take a look at this equation. F of x is equal to negative 2/3 x plus 5. And so here, I want to look at a table of x values and output values, f of x. And so what are some nice values we can plug into this function? Well, 0 is not a bad value to plug in, right? Because if I plug in 0 for x, we get negative 2/3 times 0 plus 5. And negative 2/3 times 0, well, that's just going to give us 0, and when we add that to 5, our result is 5. What's the next number we can plug in and get a nice result? Of course, we could plug in any number we want and get a result. The domain of this function is all real numbers, but what's a nice number we can plug in and get a whole number result out? Well, because of this multiple of negative 2/3, right? This is like saying take our input, multiply by negative 2, and then divide by positive 3. And so if I'm going to have division by 3 in here with my input, what I really want to do to get some nice results out, to see nice output values, is plug in things that are divisible by 3, multiples of 3. So if I plug in 3, what we get is negative 2/3 times 3 plus 5. And if I have negative 2, I divide it by 3, I multiply it by 3. Well, those multiplication and division by 3 are going to undo each other. And what we just get is negative 2 added on to 5. We get positive 3. I can plug in another multiple of 3, 6, and get a nice result out. I get negative 2/3 times 6 plus 5. And it's negative 2/3. That division by 3 is going to cancel out with a part of the multiplication by 6 and leave behind 2, and we'll have negative 2 times 2 is negative 4 plus 5. That's positive 1. If we do one more, we get 9. Negative 2/3 times 9 plus 5. And so taking this 9, dividing it by 3 gives us 3, and multiplying it by negative 2 gives us negative 6. Adding that with 5 gives us negative 1. And so these are ordered pairs of solutions to our equation, and so we can plot these points out, 0, 5, 3, 3, 6, 1. It's not on this grid perfectly, but I can tell it would be roughly out there, and we can see that the graph of this equation, these are the nice points, very, very nice to pick out points on our graph, but of course there's all the points in between. We know that we're going to have a linear function. We know the graph of this function is going to be a line, and so I can go ahead and sketch the graph there. One thing I want to mention is that we plotted 3 points here to graph this line, this linear function. It only takes 2 points to dictate a line. Right? If I draw 2 points, there's only one straight line that passes through them. And so really, if you're trying to graph an equation by plotting points, graph a linear function, it has to be linear here for this to really be true. You only need to find 2 points. Though I recommend finding a third point because it's very easy to make a mistake somewhere, and if you make a mistake on one of these points, your graph's going to be way off. If you plot 3 points and you make a mistake somewhere, it might be a little bit more noticeable. You might be able to catch yourself. So another thing I want to mention here is just some language. We see here that there's this rate of change or slope of negative 2/3. There's this initial value of positive 5. And here I just want to talk for a moment about this initial value of positive 5. This appears here as this point 0, 5, right? If I have an input of 0, I get an output of 5. That 5 is really telling us that we have this point on the vertical axis of 0, 5. Right, so here, this is 0, 5. It's what we call the vertical intercept of our line, of our function. This is the point where our function crosses the vertical axis, so we call it the vertical intercept. And it corresponds to the point with an input of 0, we get an output of 5. So it's the point obtained by inputting 0 into our function, and it's the point where our graph crosses the vertical axis. So sometimes we call that point not just the initial value, but we call it the vertical intercept. So another way we can graph linear functions, maybe more efficient than plotting points, is using the slope of this linear function, or the rate of change, alongside one point on the graph of this function. And so here, if I look at the function f of x is equal to 3 over 4x, right, this 3 over 4 is the rate of change, it's a slope. And this negative 2 tells us one point on the function, right? This is the initial value. We see that when we have an input of 0, we have an output of negative 2 on this function. It's where our function crosses the vertical axis. We call it the vertical intercept. Right? So here we have 1 point for free on the graph of our function. And what we can do now is we can use this rate of change to determine other points on the graph of our function. Right? So the idea here is that I know 1 point on my graph is 0, negative 2. And I know the rate of change between any 2 points on this line, on this linear function, is going to give me 3 over 4. Well, then what's 1 point? What's one other point that I can clearly see will give me a rate of change between this point of 3 over 4? Well, it's this point out here, right? Maybe I'll plot it in black. It's this point out here. And why is that the case? Well, if I look at the change in y between these 2 points, that's plus 3. If I look at the change in x between these 2 points, it's plus 4. And so their rate of change would be 3 over 4. So because the first point's on the line, the second point, if I compute the rate of change between the two, gives me 3 over 4. The second point must be on the line as well. And so what I'm saying here is that if I have a point, I can use my slope, use my rate of change to find other points on my line by taking the numerator as my change in y, going up 3 units in this case, and the denominator as my change in x, going up 4 units, or to the right 4 units in this case. And so we could also use this to find more points, right? So another point that would fall on our line would be out here, because I can see that if I were to go up 3 units from this point and right 4 units, we would still get a rate of change of 3/4 with another point that we know is on our line already. And so here, now that we have at least 2 points, we can graph the line corresponding to the equation f of x is equal to 3/4x minus 2. So this is one way we can graph linear functions. Okay, so let's take a moment to graph these functions, f, g, and h of x. And I encourage you to pause the video and try and graph these out first yourself, and then we can go over them together afterwards. So here for f of x, we see that we have a slope or a rate of change of 1/3, and we see we have a vertical intercept of the point 0, 1. And so here maybe I'll use purple to graph this function f. And we see we have the point 0, 1 on this function, and we can use the rate of change to find other points. We can read the numerator as the change in y and the denominator as the change in x. So if I go up 1 unit and right 3 units, I get another point on my graph. Or this point out here that I would start with, go up 1 unit, right 3 units, and end up at the point 0, 1. That's also another point on the graph of this function. And I would encourage you to take these points and plug them back into your function. Convince yourselves that they really make the equation true, belong on the graph of a function, this function. But here we've got a quick way of finding some points, and then we can sketch the line through those points. What if we look at g of x? Well, g of x has a vertical intercept of 0, -4. Maybe I'll be consistent with my colors here. 0, -4. I'm going to use pink for this graph. And a slope of 3. And this might be a little trickier because we've been talking about using the numerator as our change in y and the denominator as our change in x. But we can read this as the number 3/1. And so I can see that if I go up 3 units into the right 1, I see another point on the graph of this function. If I go up 3 into the right 1, up 3 into the right 1, I see all these other points that belong on the graph of my linear function. Because linear functions correspond to lines, I know the entire graph of my function. Okay, and this last example, here I have h of x is equal to -3/2 x plus 5. So here I know that I have a vertical intercept of 0, 5. I have a slope of down 3/2. Down 3/2, I can find another point on my graph. And so here we get a graph that looks something like this. So that's the graph of h of x. So we gave some special attention to the point where the line crosses the vertical axis, or vertical intercept. And this was because it appeared in our equation for our function, and it gave us a free point to work with already to help us graph our function. But on the other end of things, we can also find where the line crosses the horizontal axis. And this is called the horizontal intercept. Right, and so here if I look at this purple function, I can see that it crosses the horizontal intercept, or horizontal axis at -3, 0. And so that would be its horizontal intercept. We can also see that these other lines have horizontal intercepts, but maybe they're a little bit less clear. And so here, if I look at this pink line, we can determine that horizontal intercept by evaluating or figuring out when this function gives us an output of 0, right? That's something that stands out with all these horizontal intercepts is that they're the points on the graph where the output is 0. And so really, if we typically want to find a horizontal intercept, we want to find the point with an output of 0. That's what it means to find a horizontal intercept. And it's not always important to find the horizontal intercept. It's not always really useful to plug in or to figure out when we get an output of 0. But if you do that, that's really what you're doing here is finding a horizontal intercept. And so let's do that for this function here. So this pink function, this is g of x. What is this equal to? It's 3x minus 4. If we wanted to find the horizontal intercept of this function, well, what we do is we let our output be 0 and determine the corresponding input. So adding 4 to both sides, we get 4 is equal to 3x. Dividing both sides by 3, we get 4/3 is equal to x. And really this is saying that x is equal to 4/3 when y is equal to 0. Or in other words, our horizontal intercept is the point 4/3, 0. That's this point. That we have identified here on this pink line. That's what we're finding when we do something like this. So here, let's do the reverse. I have a graph here, and I want to find the equation of this linear function. So here, we notice that if we have some linear function, the equation of some linear function, we know that that coefficient of our input variable, that's the slope. And we know that that constant that's being added on, that's the vertical intercept, the y value or the output value of the vertical intercept. And so here I can see right away that this point 0, 5 is the vertical intercept. And so if this is, I'm labeling f of x, then f of x is equal to, well, I know that I'm going to have this plus 5 at the end of my function. But we can also see that the slope would be, well, our change in y between these 2 points would be minus 3. And our change in x would be plus 2, and right, our slope is the change in y divided by the change in x. This is minus 3 over 2x times x plus 5. So this is an equation for this linear function. So there are two special kinds of lines that I'd like to give a little bit of extra attention to right now. And so let's start with this example here. I have f of x is equal to 0 times x plus 3, and I want to graph this equation. So here we can use our same ideas. We see the slope of this line, this linear function, is 0. And its vertical intercept is the point 0, 3. And so it passes through this point 0, 3. It has a slope of 0. And so how do we make sense of what a slope of 0 looks like for a line? Well, here, if I have a positive slope, our graph is going up from left to right. It's an increasing function. If we have a negative slope, our graph is going down from left to right. It's a decreasing function. And if we have 0 slope, right, it's somewhere in between. It's not going up, it's not going down from left to right. It's really staying flat. The y values are staying the same. So this is the slope of 0. And so the graph of this function looks something like this. This is really f of x is equal to, and here I wrote 0x plus 3 just to really emphasize that there's a slope of 0 here. But no matter what input I plug in, 0 times that input is going to give us 0, and we're just going to get 3 out. Right? All the y values of this line, any point on this line, they're just 3. Right? So really this is given by the equation f of x is equal to 3. So here I just want to say that f of x is equal to c. In general, if we have the equation in the form f of x is equal to just the constant, really we've got a slope of 0 here, we've got 0 sets of x involved in this equation. This is a horizontal line. All the points on the line have a y value, or an output value, of c. Now what about the other end of the spectrum? What if we looked at the equation? Let's say we wanted to graph the equation. X is equal to, let's say, 4. Right, so what are some points on the graph of this equation? Well, here we're just demanding, right, so the points of an equation, they are just the ordered pairs that make this equation true. When you plug in that value for x and that value for y, it makes the equation true. So what ordered pairs make this equation true? Well, the only thing this equation demands is that the x value is equal to 4. And so I can plug in 4 for x and anything I want for y, and it'll make the equation true. 4, 1, 4, negative 13, 4, 27. These are all ordered pairs that make this equation true. They satisfy the fact that x is equal to 4. And so if I list these points out, or plot these points out on a coordinate plane, well, here I get the point 4, 0, 4, 1, 4, 2. Really, we get this line here consisting of all the points with an x value of 4. And so much like f of x is equal to c is a horizontal line, or the y values are equal to c is a horizontal line consisting of all the points with the y value of c, the graph of x is equal to some number. This is a vertical line consisting of all the points with x values of that number. So here, if I say x is equal to a, well, this is a vertical line all points on this line have an x value of a. And one thing I like to mention for this is that if we take any 2 points on this line and we compute the slope between the 2 points on this line, maybe let's do this, let's use those 2 points. Well, what do we get? Well, we get the change in y. So here maybe I'll list this out. This is the point 4, 0, and this is the point 4, 2. The change in y, maybe I'll write it as 2 minus 0, divided by the change in x is 4 minus 4. That's 2 over, not 2 over 4, 2 over 0, right? 4 minus 4 is 0. And division by 0, we said, is undefined. Doesn't really have a sensical result. And so here, the slope of a vertical line, it's undefined. And so here, another thing we can notice is that this can't be written in function notation. This isn't a function, right? It fails the vertical line test. And if I tried to write this out as f of x is equal to mx plus b, well, we don't even have a slope to write for this function. We don't have a vertical intercept to write for this function unless the function, or not this function, this equation. We don't have a vertical intercept unless this line passes through the vertical axis. Really, x is equal to a cannot be put in function notation because it's not a function. And although it's a line, it can't be written in the form f of x is equal to mx plus b.